Let me introduce Jeff Collett. Dr. Collett is a professor and head of the Department of Atmospheric Science here, and Doug Jordan is the director, corporate environmental programs of V+ Development Solutions Division of Southwestern Energy. And you'll have a further longer bio in not only the printed programs, but those that are on the live stream. Please go up to the website, go to the agenda, and you'll see the wonderful credentials of these two gentlemen. I'm going to hand it off to Dr. Collett right now. Thank you. And here's your clicker. Please welcome Jeff Collett.
Thank you, everybody. It's great to see so many people here for this Natural Gas 101. I think Doug and I have a tough act to follow, but we'll do our best to give you a little bit of background about air quality issues. I'm actually going to start by trying to give you a little bit of context about a brief history of air pollution to set the stage for talking about issues related to unconventional gas and oil recovery. So if we think back, way back, probably the first air pollution issues followed when we discovered fire. And if you look at, for example, this house, which is a reconstruction of a Stone Age house from England, you'll notice, you can't quite see the top, but there's no chimney on this house. And people lived with fires that we're told were burning 24 hours per day and generating a lot of smoke. They lived in this environment all the time. And on the right here is a photograph of a skull from one of these periods. And this is in a really interesting book by Peter Brimblecombe called The Big Smoke. It's about the history of air pollution, specifically around London. And what they've found by discovering and studying these ancient skulls is that these people had a lot of sinus problems. I get sinus problems, and so I can imagine what it must have been like to live with this, constantly breathing all these particles in. Humans got a little bit more experience, and they realized maybe we should invent a vent for this smoke, a chimney, and they let the smoke outdoors. And so things improved in terms of the indoor environment. I think maybe as a species we missed breathing smoke because one of our next inventions a little bit later was cigarettes. Maybe not our finest moment. If we jump ahead to the period of the Industrial Revolution, of course, we were changing our economy. We were changing methods of production. We were starting to use energy more widely. We knew that we should build smokestacks, and so we had these stacks. And the smoke that came out of them was almost sort of romanticized as sort of a symbol of our economic success. And so if you look at paintings from the second half of the 19th century, the early 20th century, like this Monet painting, you'll see often these sort of artistic depictions of air pollution. We went on that way for a while, enjoying the fruits of our economic success. But by the middle part, in particular, the 20th century, we started to realize some of the issues associated with pumping the smoke outdoors. And so there were a number of famous episodes. This is perhaps the most famous in London in 1952, a multi-day smog event. You can see there the photograph on the right. This is a daytime photograph in London of a double-decker bus trying to make its way through the streets of the city. There was so much particulate air pollution that it looked like night, and people had to walk in front of the buses with lights to guide them through the city. Studies of this period that lasted several days suggest in excess of 4,000 extra deaths occurred due to the air pollution during this period. This was not the only event. There were others, including an event in the small town of Donora, Pennsylvania, here in the U.S. that was a similar sort of thing, but on a smaller population scale. And these were really a wake-up call to address urban air pollution and our exposure to that air pollution. So we thought a little bit more about chimneys and said, what if we make our chimneys really tall, and then we won't be breathing all this air pollution that we're generating in the city? So we went through a period where we built really tall stacks. This is a nice example from an electric generating unit, a coal-fired power plant in West Virginia. This is a little bit over 1,200 feet tall. At the time of its construction, I believe it was the tallest in the world, and for a long time remained among the top 5 or so. This really did help to clean up air pollution in our cities, but it wasn't long after that till we started to realize that we inadvertently changed these local air pollution problems to long-distance regional air pollution problems. Last week I was in upstate New York at the International Acid Rain Conference. There was a lot of talk about the discovery of acid rain in Scandinavia and later the northeastern US and Canada in the late 1960s into the early 1970s. And this came about primarily because we were taking this sulfur dioxide from the coal-fired power plants, distributing it over long distances. It reacts in the atmosphere to make sulfuric acid. It's deposited into ecosystems far downwind of the source. It acidifies lakes, it damages forests, and so forth. So at this point, we realized that we couldn't simply invent better chimneys. We needed to address sort of the root cause of air pollution. And starting in the US, especially in the early 1970s with the Clean Air Act, subsequent amendments to that, and ongoing air pollution regulation that continues to this day, if you look at this figure, you can see that lower line shows the change in the sum of 6 common air pollutants over time. And you can see a reduction of over 60% since the beginning of this graph in 1980. At the same time, we've increased economic output by about 150%. Our population has grown substantially. So this has really been a tremendous success story in terms of improving air quality in this country, and they're very similar progress in Europe. I work a lot in China, and these days I can tell you they're on a different part of this curve, but they're going to get there too. They're starting to address some of these issues. If you look at evidence of success of this, you can look, for example, in the upper left here. These are emissions reductions in the blue and sulfur dioxide, and you can see tracking that very closely. The other lines are reductions in fine particle sulfate, which is a health hazard and also has a strong impact on visibility and haze formation. In the lower right, you can look at the improvement in the acid rain situation. Between 1985, you see that bullseye over the Ohio River Valley extending up into New England. And by the early part of this decade, that sulfate as well as nitrate deposition had been reduced dramatically in the US and also in Europe. If you don't want to think about concentrations of things, you can think about what does the atmosphere look like. This figure from Jenny Hand, who works here for the National Park Service, shows the change in some of the worst haze days in different national parks around the country. And if you compare, for example, at Great Smoky Mountains in the lower right, you can see how the worst days in 2010 are much cleaner than the worst days in 1990. And this reflects that reduction in sulfate particles and nitrate particles and others that allow us to see farther in the atmosphere. And we do a lot of work with the National Park Service, and after all, when you go to a national park and you pay your entrance fee, you want to see what's there. And so they spend a lot of time trying to understand this and how to improve visibility for their guests. So we've come a long way in terms of thinking about air pollution, and now not only do we not ignore it, it's actually a marketing tool, right, to have things be green. Especially the younger generation is really thinking about this when they're buying products. But we've seen recently some examples maybe of how not to do this. You don't want to advertise being a really green company and then you find out that maybe there was some cheating going on. And, you know, Volkswagen faces a really difficult problem now in terms of their future because they've relied so heavily on this investment in clean diesel and didn't go about it in the right way. So that's a very brief introduction to sort of the context of how air pollution has evolved and our thinking about it has evolved. We thought a lot about conventional sources like coal-fired power plants and more recently motor vehicles. Now we're really getting to what I call the unconventional sources. And those include things that tend to be more distributed like agriculture, like wildfires, like oil and gas production is something that's increasingly of concern. These are sources that are much more dispersed. There are lots of individual points of release, and we don't understand the emissions as well as we can measure, for example, coming out a single stack of a coal-fired power plant. So let's think about natural gas and what are some of the advantages and some of the potential concerns about its production and use. Well, I don't think you would find many people that would argue about its advantages as a fuel in terms of burning very cleanly. It produces many fewer emissions of things like sulfur dioxide and fine particulate matter, or PM. Because the natural gas, the methane molecules are very energy rich. They also, when you burn them, generate less carbon dioxide than other sorts of fossil fuels. And you can see a comparison there on the right. So it's an extremely nice fuel as fossil fuels go in terms of its clean combustion. But we need to think more about just the end use. We need to think about sort of the life cycle of emissions. And Rebecca talked about some of these stages up front with the drilling and the completions. And then this diagram on the left from the EPA Gas Star program shows you some of the other processes along the way from production to transmission, processing, and distribution to customers at the end of the chain. So all of these are potential points that we need to think about in terms of possible air quality impacts. So what kinds of things might we be looking at? I'm going to break these down into a few groups. One is things that might affect climate, and in particular I'm going to focus on methane emissions. Methane is, of course, the main constituent of natural gas. It's also, as you'll see, a strong greenhouse gas, so it has a lot of potential concerns if it's leaked to the atmosphere. I'm not going to say as much about black carbon. We don't see as much flaring here as a lot of places. We've worked up in the Bakken in North Dakota. There's a lot of flaring. You see a lot of soot coming off of those flares. Soot is also a concern from a climate forcing perspective. I'll say a bit about what we call criteria air pollutants. These are things that are regulated by the EPA in the U.S. because of their human health effects. And in particular, we'll talk about ozone and about fine particles, which we call PM 2.5. That's particulate matter with an aerodynamic diameter less than 2.5 microns. Just think fine particles. And then I'll say a little bit about hazardous air pollutants or air toxics. Here we're thinking about things like particulate matter from diesel combustion, different VOCs, those are volatile organic compounds like benzene, other related aromatic hydrocarbons, formaldehyde, and in some places hydrogen sulfide can be a concern, but I'm not going to really talk about that today. So let's start with climate and focus on methane. I mentioned already that methane is a much more potent greenhouse gas than carbon dioxide. This is because it absorbs a lot more infrared radiation per molecule than carbon dioxide does. If you look at a 100-year reference time frame, the global warming potential of methane is approximately 23 times that of carbon dioxide. So when we burn methane as a fuel and convert it to carbon dioxide, it's efficient. But if we're leaking methane along the way from drilling to production to transmission, we could offset that potential benefit in terms of this being a cleaner burning fuel from a climate perspective. You're going to hear tonight from Fred Krupp from the Environmental Defense Fund. They've been a real leader in organizing research on trying to understand the leakage rate of methane in different parts of the system that we saw a moment ago. Ramon Alvarez of EDF led a really nice paper a couple of years ago that looked at the leakage rate versus the years to climate benefit for fuel switching. For example, for a coal-fired power plant to replace that with natural gas, or a diesel vehicle or a gasoline-powered vehicle. And these figures here show you some information about that based on his estimates. And what they show is that at the left side of these figures, at the y-intercept, that tells you how low the leakage rate has to be for an immediate benefit to switching from, say, coal to natural gas. And as you look to the right, moving out, these are at different time horizons. So what this really does is raise questions about, well, what are acceptable leakage rates in terms of a climate forcing perspective for a fuel switch from one fossil fuel to natural gas in different applications. So this has been a real focus of attention over the last few years, trying to better understand those leakage rates. People have gone out and made a lot of measurements of this in the field to try and understand it. they've used, and you'll hear these terms, bottom-up approaches and top-down approaches. A bottom-up approach is where you go out and you try and measure, sometimes even down to an individual component scale, but maybe a facility scale, and you basically add these emissions together to try and come up with the total, and you compare them to some estimate, or what's called an emissions inventory of methane from these activities. A top-down approach is a complementary approach where you literally try and look at the concentrations, for example, in the atmosphere, and use those to come up with what the emissions had to be to produce those concentrations. So, for example, you might fly an aircraft over a basin like the DJ and look at the upwind and the downwind concentrations of methane and try and figure out how much methane was emitted in that basin. That gives you sort of a top-down constraint on the total emissions. Now, of course, natural gas production is not the only source of methane. In Weld County, for example, we have a lot of livestock feeding operations. So there are some issues to sort out in these top-down approaches as well. Some of my colleagues here at CSU have been very involved in these methane emission studies with EDF. You'll hear more about those tomorrow in one of the panels. But I just included here one example. This is a very recently concluded and published study led by Anthony Marchese here at CSU, working with EDF and industry partners to look at the loss rates associated with gathering systems and gas processing facilities. And you can see a figure here that shows a lot. They made a lot of measurements. They looked at what the leak rates were as a percentage of the throughput through these facilities. And they found out in the end that there's about 0.5% of the total throughput that is leaked from the combination of gathering and processing of natural gas. And most of this actually looks like it's coming from the gathering facilities, less from the processing facilities, and that gives us an opportunity to think about maybe where to target tightening up emissions if we want to bring those leak rates down in the future. All right, let's talk about some of the other regional air pollution issues. We'll talk first about ozone. The chemistry of ozone is very complicated, and I could bore you with pages and pages of equations, but I picked this sort of simple diagram to try and illustrate the essence of what's going on. So at the top of this diagram in the upper left, you'll see basically two coupled cycles. There's a small circle on the top, and it's reproduced on the bottom. This is a cycle that involves nitrogen oxides and sunlight and oxygen and ozone. And basically reactions of nitrogen oxides with sunlight and ozone cycle round and round, and they generate a certain amount of ozone. But there's a cap to how much can be produced this way. The way that you really can generate a lot of ground level ozone is to have not only nitrogen oxides, but also these VOCs, these volatile organic compounds. And that's represented by this bigger cycle in the center of the diagram. You have volatile organic compounds which are attacked and react in the atmosphere, and they produce free radical species that react with nitric oxide to convert it to nitrogen dioxide, which the sun can then break apart and generate atomic oxygen, which reacts with O2, the oxygen we're all breathing, to make ozone. And it's really the coupling of these cycles that can generate very high concentrations of ozone. The efficiency of the coupling of these cycles, though, depends on a couple of things. It depends on the relative amounts of these VOCs and NOx, and it also depends on the particular type of VOCs you have present. There are hundreds, thousands of different individual VOCs released to the atmosphere. Some of them are very reactive and some are not so reactive. And I put together a little table here to give you just a few examples of the maximum reactivity of these compounds towards ozone production. And at the top here I have methane, which is our main constituent in natural gas. It's relatively unreactive. It doesn't really contribute much to ozone production on a local, urban to regional scale. It's more important on a global scale or a hemispheric scale. If you go to something bigger, like in the middle there, you have N-pentane. This is a 5-carbon compound. This is also emitted by natural gas and oil production, but also by other sources, including combustion sources. you can see it's quite a bit more reactive if you look at those ratios of the reactivity. And then we can go to something like isoprene on the bottom. Isoprene is actually a naturally emitted compound that comes from many plants. It's extremely reactive, and it can contribute a lot to ozone production. So when we think about sources of VOCs to the atmosphere and how they affect ozone, we need to think about not only the amount of those VOCs being released, but also their composition, which affects how much they contribute to the ozone chemistry. If you go around and you take a look at different air basins and look at the VOCs that are present there, you can get an idea about the influence of different types of sources. And one way that's been used to get a handle on the influence of emissions from oil and gas is to look at a ratio of two of these 5-carbon pentane molecules. Plotted in the upper left here is I-pentane, and N-pentane is on the x-axis. These are just different arrangements of those 5 carbons in the molecule. And if you look in an urban area, you tend to find a ratio that's bigger than 1 if you're dominated by combustion sources. But if you look in an area that's dominated by oil and gas emissions, or you look directly at those emissions, you find that that ratio tends to be below 1. So this has been used, for example, in this paper by Jessica Gilman here on the Front Range to look at sort of the relative contributions of different sources of VOCs to the atmosphere. We've used this ratio as well in our work up in the Bakken and other places too. We know, although we don't understand fully yet the extent, that these VOCs and the NOx that come from oil and gas production and use contribute to ozone production. We don't know exactly how much that is, and that's a very active area of research. Some of you might have seen the summer before last a lot of aircraft flying very low over the Front Range. You wondered what those were. Those were research aircraft that were trying to study this issue about ozone production from all different kinds of sources here on the Front Range. There are some areas where we have very clear evidence of strong impacts of oil and gas production on ozone. One is in the Upper Green River Basin in Wyoming, where there were severe winter ozone episodes. This is a region without many people, but in the winter you have a very shallow mixed layer. You have snow on the ground, you have sunlight, and so you trap the emissions very close to the ground. You have reflected sunlight, which almost doubles the illumination, and you drive a lot of this photochemistry very quickly, and you can generate high ozone concentrations as shown in this diagram. Another issue that is of concern potentially is the formation of fine particles. These, remember, are damaging to human health, but they also impact things like visibility in the atmosphere. One of the main areas of concern is emissions of nitrogen oxides. Those can react in the atmosphere to make nitric acid. These are both gas phase compounds. But the nitric acid can react with ammonia, which comes mainly from agricultural sources. Ammonia is also a gas phase compound, but when it reacts with nitric acid, we make small particles, smaller than a micron in diameter. These have very long lifetimes in the atmosphere. They're very similar in size to the wavelength of visible light, which turns out to mean that they are very effective at scattering light and reducing visibility. So you can see, for example, here this photograph from the Bakken region of this haze that's sitting over that region in the wintertime. So I showed you a few minutes ago some examples of how across the U.S. things have gotten much cleaner in terms of fine particles. This plot, which comes from the National Park Service, also looks at changes in fine particle ammonium nitrate particles. And the blue colors here show reductions in nitrate concentrations across the U.S. over a 12-year period. This happens to be for the month of March. And you see much of the U.S., we're seeing remarkable reductions, averaging a few % per year over more than a decade. But you'll notice there's some outlying regions. In particular, I point out this region up at the border between North Dakota and Montana, which corresponds, if you look at that diagram on the right, very closely to the Bakken oil field. And we spent a couple of winters up there looking at this issue and find that indeed the emissions of NOx associated with the growth there, the oil production and so forth, are resulting in the production of these fine ammonium nitrate particles, which contributes, for example, to a haze issue here, for example, shown in Theodore Roosevelt National Park. Let me just close before I turn things over to Doug by saying a couple brief things about air toxics. Again, here we're concerned about things that are carcinogenic or in some way harmful to human health. This focus is often on gas phase compounds like benzene, but also particulate matter from diesel is known to be a health hazard as well. These emissions certainly vary by operation type. We're actually in the midst of two big studies looking at air toxics emissions from different stages of oil and gas activity, for example, drilling versus fracking and so forth. Some of these compounds come from the deposit. We heard already about how benzene exists in the deposit as part of the oil, and so some of that can be released from there. Some are released from other sorts of ancillary activity like diesel generators or natural gas power generators that are providing power to generate that power on the site for drilling and fracking and so forth. But they also have other sources like the car that most of you probably drove here and today is emitting these kinds of things as well. When you go to the gas station, there are emissions of these kinds of compounds. We've been talking mainly about issues that are global in scale, like climate, or regional in scale, like ozone and fine particles. Air toxics are really more of a local scale issue, if they're an issue at all. Some studies have shown that these concentrations fall off very rapidly. For example, I included here a figure from a study from the University of Nevada, which shows within about 100 meters of a condensate tank, the concentrations of benzene and other compounds being emitted from that tank were down to about background levels. Now, that doesn't mean that they aren't contributing to concentrations in the atmosphere, but the highest concentrations are going to occur very close to those sources, and they tend to get dispersed rather quickly as you move away from those sources. In the upper right here is another figure that shows from that same University of Nevada study a breakdown of the source contribution of different source types to these compounds. And what they found, for example, for pentane, when you were close, in the residential area close, this was actually in the Barnett Shale region in Texas, when you were close to this activity, you saw that the condensate tanks were a large source of things like pentane. But if you looked at something else, an air toxic like benzene, that was actually dominated much more by heavy-duty diesel traffic than it was emissions from the condensate tank. And so this is an area of active study, including the work we're doing to try and better understand the source strengths of different types of sources to these compounds that may be of concern as far as human health. So I think I'm going to wrap things up there and leave some time for Doug to talk a little bit about mitigation and other issues from the industry side of things.
Oh, there it is. Well, howdy. My name is Doug Jordan, and I'm with Southwestern Energy. I'm the director of our corporate environmental programs. Informally, I'm the company airhead. I've been a practicing environmental professional for well over 30 years, so I'm also known as Air Jordan, and I am older than Michael Jordan, so I think I can claim that title over him. We'll move into a discussion on mitigation and air emission controls. This first slide, I kind of wondered why I had to put it up. But you noticed earlier that Anadarko had a similar slide, the forward-looking statements. It basically says, hopefully, you won't take anything I say to influence your decision on whether or not to buy company stock, et cetera. The only reason I wondered why I had to have it in here was because I figured I was presenting to a lot of college students. And so if you had any money left over after books and tuition, it was probably going towards pizza and beer and not company stock. But I had to have that in there. This is a little bit of a footprint of Southwestern Energy. We are a vertically integrated company. We operate our own fleet of drill rigs. We have our own frac fleet. We have producing wells. We are the primary producer in the state of Arkansas. And we also have a midstream or gathering and processing arm. We are also, right now, the third largest producer of natural gas in the United States, and so we're pretty proud of that. Of course, that also means that we just don't have a lot of other acreage that has oil and condensate that a lot of the other companies have gone over to. I would like to go ahead and mention that at the bottom right of the screen is this formula, and I'll go ahead and explain that formula because it is, if you will, our mission statement or our vision statement. And if you can't see it, it's R squared over A and then kind of an arrow upward to V plus. And what that means is the right people doing the right thing, wisely investing the cash flow from our underlying assets will increase value plus. And that's something that we apply, in all of our business activities, including the environmental arena. Now, I'm going to talk today about air controls that can be used in the oil and gas sector. And I'm really going to talk more about the controls that apply from production through the transmission point, okay? This is a 101 course, so I did want to keep it pretty general and pretty simple. But also, I got to spend about 4 weeks recently out in the field with a couple of individuals from Colorado State University. Clay, who just received his PhD, his cohort Tim, who's still waiting on his PhD, and their sidekick Cody, who just started up his master's program. And after spending several weeks with them, I kind of thought, if they're coming to this thing, maybe I better use pictures, because pictures are worth 1,000 words. So Tim, Clay, thank you all. So we start off here with a drill rig. This is what we call our rocket rig. And Swin is not the only company to do this. I think the majority of the drilling companies are starting to move this way. And, before we have the well that can generate emissions, we have to drill the well, as Ms. Rebecca pointed out earlier. And early on, initially, the drill rigs were powered with diesel fuel. You burn diesel to basically create electric power to operate your drill rig. Well, what we've done here is we have converted our engines to where what they're called biofuels, so they can burn both diesel and natural gas. And the benefit of burning natural gas is that you use less fuel, but you also reduce your emissions. And really what you're reducing are your criteria pollutant emissions, your NOx, your CO, your VOC, and your SO2. So before we even have a flowing well, we're actually implementing controls on the drill rig to minimize the emissions. Here's a picture of the completion flowback. So Ms. Rebecca talked about how you drill the well, you frack the well, and then you begin the flowback. And that's where you start bringing back the water and the sands that don't stay, in the well bore, and you're starting to get that gas to flow back. And there's a couple of different scenarios that we'll look at. The first one, and this is really the old-fashioned way, where it was not uncommon to where when you started your flowback, you would take the flowback possibly straight into a tank. And so what you see there are essentially a frac tank, and basically what they have on it is what they call a gas buster. Well, the gas buster is nothing more than a device that diverted the water into the frac tank and the gas up into the atmosphere. So you were venting anything that was coming out of that well straight up into the atmosphere, no controls. The other thing that you would see is where people would use a flare. And so on the left, you actually see what we would call a pit flare. They're basically routing, the gas stream out to a pit with, through a pipe and essentially a flare at the end of that pipe. Or you also see kind of the early movement towards controlling emissions from those flowback, where you would capture the gas and route it to a flare. So here you were burning any of the methane coming out, but you're creating NOx and CO and VOCs. So the next step on reducing emissions from the flowback is what they call reduced emissions control, or what people also call green completions. The EPA in 2013 passed a rule, the NSPS Quad O standards, which really require the reduced emission completion technology to be applied to gas wells. And this year, and it's open for comment now, they have proposed to expand these REC requirements to oil wells that are hydraulically fractured as well. So what they're really going after is no more just that direct venting to the atmosphere. So the REC control requirements that we have are that you initially begin flow, you can vent for a period of time, but then you are encouraged to route your gas to the sales line as quick as possible, but in between, you can use a flare if you need to. So the REC provision still allows the use of a flare to be compliant, but again, the emphasis is capturing that gas and getting it into the sales line so that you have no emissions. One of the things that we were able to do at Swin Gas is what we call the REC Plus, or what we call our Swin Gas Capture. And the Fayetteville, which is where our primary production are, is what we call a low pressure basin. It's like 40 to 60 pounds on average. So there's not a lot of energy down in the ground to really help bring that water and sand back up. So what we do is we bring in a compressor engine, typically about a 1500 or so Caterpillar engine, and we actually use gas available at the site from one of the other wells to basically pump the gas down into the reservoir and energize it and pressure it up. And that way, instead of flowing back at 40 or 50 pounds, we're closer to 1,200 pounds when we start that flow back of the water, the sand, and gas. As that mixture comes up through the Christmas tree, and so I'm starting out the picture in the upper left, it comes out of the Christmas tree, goes to the next picture to the right. We run it through a sand separator, and the sand separator is there to drop out sand because we really don't want to run that through our equipment and through the system. It just it's not. I mean, it's great sandblasting material, but you don't want to eat up your equipment. From that sand separator, the gas liquids go into the separators. We're in the top right, and those are what we call our fat boys. Those are oversized separators that we installed that really allowed us to capture that gas and water, that high flow in the initial phase, and be able to separate the gas and take the gas straight into the sales line. And then the liquids off the bottom of the separator, we route to a frac tank, which is what you see in the lower left corner of the picture. And we run that liquid through the frac tank so that we can measure how much water we're getting, and we can control the water as it goes into a surface impoundment, which is what you see in the middle and the bottom. And we do that so that we can collect and reuse and recycle that water in future frac jobs. And then I mentioned that from those fat boy separators, the gas is routed to the meter, which is the picture at the lower right. That's where it goes into cells. And so one of the things that's different about the gas capture that we employ, you do not see a flare here. We don't use a flare with our reduced emissions completions in the Fayetteville Shell. And then this is some information that we have shared with the EPA Natural Gas STAR program. We've been a participant since 2006. And we were actually the production partner of the year back in 2011. And it was our early implementation of the reduced emissions completions or gas capture that really helped us achieve that recognition and the award. The Marcellus Shale up in Pennsylvania is a higher pressure formation, more in the 500 plus pound range. Those wells flow a lot higher. So what you see there is a big difference in the numbers. But basically by employing this gas capture technology, and it's kind of all packaged there in that picture to the lower right. In the Marcellus, we estimate that we've recovered over 152 million cubic feet of gas by employing this technology, which is over 3,000 tons of gas, okay? And in the Fayetteville, we recover over 16 million, and I apologize, that was wrong. It was 152 million cubic feet of gas per completion, not in total. And the 16 million is for the Fayetteville. Again, lower pressure, less production on those Fayetteville wells, but still a significant reduction. What in the past we used to be able to send to the atmosphere. One of the items, and I'm kind of trying to go through the chain from the wellhead more towards through processing, pneumatic controllers. Pneumatic controllers are devices that use natural gas to open and close valves, okay? They're used for liquid level controllers, process controllers, et cetera. And they've been used for a long time because gas is available at a well pad at a compressor station, at a transmission station. And remember that a lot of these facilities are located in areas where you don't have power available. And so gas is there and it's, easy to use. So the first kind of pneumatic device that you have is what they call a high bleed, a continuous high bleed device. And a continuous high bleed device is defined as a device which continuously bleeds over 6 standard cubic feet of hour per gas. A low bleed device is one that bleeds less than 6 standard cubic feet per hour, not year. That's a typo on that slide. So the low bleed would be a mitigation to a high bleed. And then the next step down from that is what they call the intermittent bleed controllers. Those are the ones that only vent gas when it's actually actuated. So they're not continuously bleeding like the other. They just go psh, psh when they operate. And so the first two pictures you have there are pictures of those snap-acting or intermittent controllers. From the intermittent controllers, the next level would be go to what they call zero emissions systems, or there you're either using an electronic type controller if you have electric available, or you're using an air system. And finally, you have the no bleed, which also have the zero emission. And I kind of show a picture at the lower right, and what that is a fuel cell. At Southwestern Energy, we actually put a fuel cell at one of our well pads so that we could actually operate an air compressor and run our pneumatics based, instead of using natural gas, we're actually using air. It wasn't very cost effective, but we did prove that it does work. The next source that we have are what we call pneumatic pump controls, and at a wellhead, you will typically have chemicals at your site, and you will inject typically corrosion inhibitors or algicides down the wellbore to keep algae from growing or corrosion from forming. Or you also use methanol, and the methanol you typically use more in the colder months, to keep everything from freezing up. And again, typically those pumps are driven by natural gas. And if you use the EPA emissions factor for these chemical pumps, they estimate 13.3 standard cubic feet per hour whenever they're operating. And what I have is a picture for you. On the left side is a picture of a methanol pump that's tied to that wellbore. And I apologize, it's hard to see, but right in front of the of that chemical tank is the small chemical pump. So every time that's actuating, it's releasing a little bit of gas. Well, one of the things that you can do to help minimize the emissions from those types of chemical pumps that's pretty cheap is to put a thermostatic controller on there, so that instead of using a timer to inject the methanol, you actually have a thermostat that when it drops below a certain temperature, it actually actuates the pump. So that's a mitigation control. Now the other way to minimize the emissions, either off of that type of pump or the corrosion pumps that tend to be used year-round, are to go to solar. And so here you have a picture to the right of two corrosion inhibitor tanks, and those are solar-powered pumps. One of the challenges that the industry faces with these solar-powered pumps is that most production sites are not difficult to get into. Most of them are sitting in somebody's pasture. Most of them aren't fenced in. And for some reason, people seem to want to take these solar panels and batteries home for souvenirs, make the cars work, I don't know. So what we have to do in that, to the far right, you see a stainless steel box. That's what is protecting the battery from being used to drive somebody's deer feeder. A little bit on storage tanks. On the storage tanks, again, depending on what it is that's going into the storage tank, will change your emissions profile and will change the types of controls that you need to apply to it. So, the process diagram on the left, you have coming from the well or it from a pipeline, perhaps a gas liquid mixture. It goes into a separator. You're dropping the liquids out. It's going over to a tank. Now, if it's produced water that's going to a tank, there's probably very little emissions associated with that storage tank because it is supposed to be primarily water. You could have some methane carryover, some minor hydrocarbon carryover, but it's going to be produced water, and those typically aren't controlled. But in areas that are rich in gas where you drop out condensate or otherwise natural gasoline, or in areas where you are going after oil, you are actually putting hydrocarbons, hydrocarbon liquids into that tank, and that's where you have the potential to have VOC emissions from those storage tanks. So one of the control devices that's really common for your larger storage tanks handling pretty large volumes of condensate or oil are what they call vapor recovery units. And the NSPS Quad O standards that were promulgated back in 2013 essentially require this type of control on tanks that have more than 6 tons per year of VOCs, okay? There were also some niche apps, subpart HH and subpart HHH rules that were promulgated back in the 1997 timeframe that went after the air toxics, the benzene, toluene, ethylbenzene, xylenes that could come off of big condensate tanks that also required similar controls. So the VRU is there to actually collect the vapors off of the storage tank as opposed to them being vented to the air. And then it is either routed to processing or to the sales line, fuel gas, so it can be used as fuel for the facility, or it might be sent to a flare. And these are just two different pictures of what a vapor recovery unit looks like. It's basically a separator to drop out any liquids, and then you have typically an electric powered rotary vane or screw type compressor to compress that captured gas and move it to the next step. The other type of control that you see for storage tanks, and these can be downstream of the VRU or they can just be downstream of the storage tank, again, depending on the volumes and the pressures, are what they call flares or combustors. And so the picture on the left is a big enclosed combustor connected to some sizable tanks. The one on the right looks more to be like a well pad tank and a much smaller flare. So again, for storage tanks, it's by and large either vapor recovery and or flare/combustor. Glycol reboilers are what are used to get water out of gas. So whenever the gas is coming out of the ground, it's got water in it. That's not good to send to the pipeline. You can't burn it in your house. So what you do is you run that gas through a glycol reboiler. And so it goes, the process diagram on the left has the initial tower that the gas goes through. Glycol is ran through there to pull out the water. In the process of pulling out water, it also pulls out or absorbs methane and other hydrocarbons, especially BTEX. Once the glycol comes down to the bottom of that tower, it needs to be regenerated. So you send it over to the reboiler. And so the reboiler is just like a big heater with tubes inside of it, and you're heating up those tubes, and what you're doing is as you're running that glycol through there, you're driving out those gases, okay? And typically those gases are vented out of the still column vent. And it's kind of hard to see, but the picture to the right, the really tall device, that's the scrubbing section. The two horizontal sections, the one that's more silver is the reboiler. The one that is lower to that is a flash vessel that we'll talk about in a minute. But then you see two stacks coming off of it, one that's got a cone on it, and that's the firebox, from the emissions for burning fuel to heat up that glycol come out of that. But then the other one with the tube coming off the top, that's the still column vent. So that's the vent that is really where you're looking to have potential methane, VOCs, and air toxics emissions coming from. In terms of controls, there's some controls you can do on the process side to minimize your emissions from the glycol reboiler. Probably one of the easiest things to do is to install a flash vessel. And so here, the flash vessel is the upright vessel on the left side of that entire unit, with the reboiler being the horizontal unit. And what you can do is you can route your rich glycol into that flash vessel before it goes into that glycol reboiler. And what it does is there's a pressure drop that occurs, and it allows the gas to come off before it goes into the reboiler and then just goes potentially into the atmosphere. Likewise, you have a chemical pump that is used to circulate that glycol between the scrubber and the reboiler. And it actually, too, has VOCs entrained in it. So you can run that gas through that flash vessel to, again, strip out that gas before it gets into the reboiler and goes to the atmosphere. The gas that's recovered from that flash vessel can be recovered as cells, it can be used as fuel gas, or it might go to a fuel or combustor. Another process improvement you can do is you have what they call a glycol circulation pump. The most common one in the industry is a Kimray pump. It uses pressure from the system to drive it, okay? But it sends that liquid that's rich in gas potentially to the flash vessel or into the Glycol Reboiler. So what some people do is install, if they have electric, they'll install a electric compressor. And that electric compressor, you're not using that liquid, you're not generating an additional load in that reboiler, which creates more emissions. On the still column itself, basically, the first thing you look at doing is putting a condenser on. And so what you see in the upper right is a picture of a condenser, and there's also a condenser on the lower left. They look like a lot of lines, like pretty much like a radiator. These were really first required by the NESHAP's rules back in 97. And so since they were targeting benzene, toluene, ethyl benzene, xylene, a lot of people call them BTEX busters or BTEX eliminators, even if they're at a site that is really more for VOCs. That condenser, you could also route the gas, if you're not recovering everything out of there, to a flare for combustion. On compressor engines, Colorado State, you ought to have a lot of pride in your engine testing lab. You all really advanced a lot of the knowledge about combustion chemistry in engines and really helped advance the controls. You have rich burn engines, which really tend to burn more fuel and create more air pollution, and lean burn engines, which are very lean. You use pre-combustion chambers, high energy ignition systems, high pressure fuel injection, all projects that were worked on at CSU to really help lower things like NOx emissions. You have the opportunity to install catalyst. On the rich burn engines, you use non-selective catalyst, which reduces VOCs, NOx, CO, and VOC. And on lean burn engines, you use an oxidation catalyst to go after CO. Okay. I was just going to mention the last thing is kind of the newer wave, and that's going after the equipment leaks, where people are using these optical gas imaging cameras to go out and find leaks. So that's kind of one of the newer technologies to really go after methane. So thank you very much.
I wanted to leave time for questions. So I wanted to leave a couple minutes for questions. Is there anybody in the audience with a question? If not, I have one on the event app. I think there's one over there, Jane. We're going to try to stop in about 2 minutes, so we don't have much time. It should be on.
Okay. I'm Wes Wilson. I have a question for Dr. Collett. If we could follow up a little bit more on the methane leak and climate. I think you'll find that the EDF saying it needs to be less than 3.2%, they've updated that because they're not just looking at the 100-year heating factor. Probably more importantly, though, when CSU came out with the low leak rate of less than 0.5%, you're well under either one. But that contrasts significantly with what was found from the top down of some 4%. And I'm wondering if you're aware that the inventor of the instrument, Touche Howard, says it's not being used properly and it's consistently recording low concentrations when they are higher.
Jeff, do you have an answer?
Yes, it's a lot of parts to that question. First, let me say that the study that I reported on, the 0.5%, is only the gathering and processing. So it's a piece of the overall supply chain, and we need to integrate the total loss across all of that. So you wouldn't necessarily expect that to agree with the top-down, but still there is a disagreement between bottom-up and top-down estimates that we don't fully understand. There is an issue that's been reported with some of the measurement equipment that wasn't, to my knowledge, the type of equipment used in this particular study, where they were actually doing releases of tracers and measuring things open versus this capture device that you're alluding to that had some issues with the measurement. But I'm aware of that issue.